Okay. So good morning. Yes, I think today, we have finished one part of that is we have proved that stress tensor. See, when somebody says stress tensor consists of 9 components written in a particular form, matrix form 3 by 3. That is called stress tensor. So, it is not a vector, it is not a scalar, it is a stress tensor. Stress tensor is symmetric. One is we have proved that it is symmetric. So, that is a important fact, and please now take a plane. See, in your undergraduate you must have done plane stress problem. Plane stress means stresses for bodies which are very thin. One direction is very small compared to the other two direction, and all the loads are applied in the same plane. Like this paper, sheet of paper. This paper is there, or let me put it urgently. This paper is there if all the loads are applied only within the plane. Okay, nothing, and this is very thin. This is one kind of problem. So, such a problem is called plane problem, and there is a special name to this plane problem, because what will happen if all the loads are applied within the plane only, nothing is applied perpendicular to this plane. No load is applied perpendicular to nothing. Like you have in our buildings you have vertical walls. Normally no transverse load is applied to the wall. They are subjected to loads in its own plane. You have membranes, you have balloon. Of course, balloon is of this, but if you take a very big balloon, so if you take a small region, that can be considered plane, and you will find that it is subjected to, there is no load perpendicular to the, no, balloon, there is a pressure inside, pressure is acting inside, no, balloon is not the. Think of some example where you have loads which are applied only. In that case, all the stresses out of 9 components, of course, there are only effectively 6 components. So, after 9 components, only 3 remain for this problem. That means, all these stresses will be, if this plane is in xy, so there will be sigma x, there will be sigma y, tensile or compression, and there can be also shear. The element can deform its shape. So, there will be tau xy or tau yx 3. So, such a problem is plane problem. Now, plane problem you have done already. So, but for a plane problem, at least draw, that means it is such that you have this point P and you have come to this point Q. So, the coordinate of P is, let us say 0 0, coordinate of Q is dx dy. Yes, thank you. So, and then it is a finite size element, not an infinitesimal element. So, we can start with, so I mean why I have taken this, just to show you, even in simple case. So, there will be, this is a negative x plane, by the way, this is your x and y. So, this is a, of course, I should have drawn it here, I have given here it 0, but it is okay, for because okay. These mistakes we do. So, then this one will be sigma x or tau xx, and then there will be shear on this will be in the, because this is negative plane. So, positive will be in the negative direction. So, it has to be like this. So, this is tau xy. then this one is another negative plane, negative y. So, there will be sigma y, and then shear will be again in negative direction of x. So, this one will be tau y x, and you see this x y and y x, they are both coming and to this. So, they will always be not only equal, but complement. It is called, they will always be pointing to a common point, common corner. So, this is important. It is not that you draw everything in a clockwise, anti-clockwise manner. Element will rotate, yes, because this element has to be in a state of equilibrium. So, now then we have, this is a positive x plane. So, here you will have sigma x plus a small increment, and increment can be written as derivative of x with respect to x, because you are moving in x direction. How much you have moved? You have moved delta x. So, this is the simplest approximation, and this is a very first term of approximation. Actually, there are more terms in this. Any approximation, higher order terms also come, not only just first derivative, second derivative, second. So, but we are taking only, stopping here only. Then shear will be like this, positive. It is a positive x plane, so it must be in the positive direction, positive coordinate direction. So, this one will be again tau x y plus some increment, and again from here tau x y was here. So, from here again it is the same rule, tau x y del x dx. Then you go to y plane, and it will be sigma y plus del sigma y by del y into del y, and then there will be a positive shear. In fact, everything is positive. This shear also is positive. It is acting on negative plane. Okay. So, do not say negative shear. This is a positive. So, you can now see the directions, and then this value is tau yx plus del tau yx by del y into dy. So, anyway, this is a simple element. It is a 2-dimensional. It is called 2D. It is not 3D, 2-dimensional plane. And this plane, such a problem where all the loads are confined to a plane and all the stresses also are in the same plane now that are developed. Such a problem is called plane stress problem. So, it is not only plane, but it is called plane stress. PLANE, plane stress problem. So, we say that this body or this sheet or this body is in a state of plane stress. So, this is a planar. Now, for this also you can prove that tau x y equal to tau y x, because this will be much simpler, but you please do it. Take moment about any point in this element, and then prove that tau x y equal to tau. This will be simpler, because you do not have to worry about forces acting in 3 dimension. These are all in 2 dimension. The other thing is, now since we have got tau x y equal to tau I j equal to tau j I, any, this one we have proved. So, we had written the equilibrium equation, sum of all forces in x direction. So, you see the first equilibrium equation had the second subscript always x, always x, no, because in direction x, that is how we were writing. So, yesterday we had written, but now since they are, so I can also write, it is not necessary now, we can also write first equation as del tau xx by del x plus del tau xy if since it is symmetric, xz plus bx equal to rho times u double dot. Now, this similarly you can write the other ones, but I just want now since it is there. So, I can write this in tensor notation now tau ij. See, summation is over which one? X is no first subscript is now common, first subscript is not changing, x y z, summation is over second subscript. So, it is j, summation is over. So, tau ij and summation is over j, and then again differentiation also with j. So, I can write tau ij j plus bi, because x is I, x is not changing, x is not changing, see the first subscript is not changed, see here x, here x, here x, and this also is x. So, it is not changing. So, it will be I equal to rho u I double dot. So, it can be written like this also. Yesterday we had written some j I comma j, j I comma j we had written. Now, it can be written in this looks neater, tau ij j, j I instead of writing like that you can write like this. So, this is our equation of equilibrium. These are this itself will represent my equation of equilibrium. So, please practice and see, there are number of books. For example, our now equation, this algebraic equation, simple, A matrix multiplied by x vector equal to B load vector. A matrix means A11, A12, A13 up to A1n. Last one AN1, AN2 up to ANN. There are these many coefficient. Square matrix is starting from A1, is it not? N equations in n unknowns multiplied by x1, x2, x3, x4 up to xn equal to right hand side B1, B2, B3 up to Bn. How will you write down? It can be written as simply, that is Aij, coefficient is Aij, Ij you take any number, not necessarily 3, multiplied by, where is the summation going? It is over j, first one, multiplied by j. See, j will be summation. So, ai 1 x1, ai 2 x2, ai 3 x3, first row I am talking of, first keep I constant, change only j, j you take from 1 to n. So, you will develop the first row equal to B1, B1 there is no summation. So, it has to be I only. So, Bi. So, a system of equation, algebraic system of equation can be written simply by this, simple. Of course, in matrix notation this is written as A, this one is called A, this one is called x like this, it is a vector equal to B. So, you have, there is one more notation. So, there is a matrix notation, there is a tensor notation, and there is a dyadic. Some people, I have seen some books, they are also expressing things as DIDAC, dyadic notation. I will show you some books, but I do not know how to write. So, this is okay. Today is 6th lecture, na? Okay. Then let us come back to our original where we left. We would like to now study little in greater detail a thing, because as a designer we are interested in the maximum value of stresses that develop at any point under the given set of loads. Not just stress, but we want to know at any point what is the maximum stress, because now you know at the same point by changing the orientation of the plane the value changes. In which direction that becomes maximum, in which direction the normal stress becomes maximum, in which direction the shear stress becomes maximum. Both can become, both can become, but it so happens that both do not become maximum simultaneously. So, there are two directions, one for normal stress and one for shear stress. When they become maximum at the same point, you are changing the orientation of, there is a stress vector that is acting on this plane, that is the value is changing. It has got two components, one normal, one shear. Now, you will find that for some orientation this one will become maximum. So, this direction where the normal stress becomes maximum is called principal direction, principal, PAL, just like principal of the school, principal direction, main direction, important. So, that is a principal direction, and when the shear becomes maximum, now go on rotating this and you find that this shear becomes here, this direction means direction is this, normal to the plane, but then the value of this shear is maximum. So, that direction we say maximum shear direction, we do not say principal, we do not say principal shear also, no, we do not call it principal shear, we just say maximum shear direction. Principal is, I think, attached to, if I am right, I will have to check again, sometimes I forget. Yes, principal is, we call it only for normal, when the normal is stress. Okay. So, let us try to do something on the, so you have this a inclined plane, and on the inclined plane you have this a stress vector Tn, which can be decomposed into three components also. Of course, these three components are not normal and shear, these are just in x, y, z direction. You can also decompose into normal and shear direction. So, this is 6th, 2. Okay. And so, this is the plane, inclined plane on which this stress vector is acting, while on the 3 coordinate planes these are the stresses which are acting. So, I have done this plus this, I have not drawn this one on the same element, actually it is acting on the same element, it is to be superimposed, it is only one element, but only thing if I draw it here it will become dirty, it will not be clear. So, this plus this, and these are on the 3 coordinate planes, these are the stresses. Okay. Then, so if n is my principal direction, let no shear, so principal, so this is my n, this defines my principal direction. So, I am changing my plane, and let us say this n is principal direction. If this is my principal direction, so I construct, I have construct my plane perpendicular to it, and I get this. Obviously, if it is a principal plane, then there will be only one single component, no shear, but again this single component also can have 3 components. Single normal can also be split into nx, ny, nz, that also Yes. Only thing is that yes, there is no component in the plane of the, if you take component of this in the plane, no, nothing, only one perpendicular total direction is this. So then we can write down T and X, T and Y, T and Z as, let us say, sigma star is the value of the principal stress, So sigma star is principal stress. Maximum. So I can take the component of this XYZ component like this 3. Is it okay? This one, because cosine of angle between n and x, cosine of angle between, just take the component. So this is one set. Now I want to write down, this is written is all right, is scalar form. I want to write down in matrix notation. So what I do, I expand this, I make a square matrix and write sigma star only on the diagonal, rest all 0, and then ln x, ln y, ln z here. Is it okay? Because this multiplied by this, I get this. Second one, this, because then this multiplied by 0, this multiplied by 0, 0. Second one, this multiplied by here 0, then this multiplied, yes, it is sigma star ln y. So this one has been expanded into a 3 by 3. It is written in matrix notation, nothing else. This is scalar, this is scalar form, and this is matrix. This is in matrix. There is no other. Of course, this element is in equilibrium, and you also have your normal stresses which are acting here on this plane, these are the 3 negative planes. There are coordinate stresses 3, 3, 3, 9, 9 components are acting. Okay. So this is okay, clear? So I can also write, since I have this coordinate stresses acting, so these 3 components can also be written in terms of coordinate stresses, and that is, so let us call this as A, and our standard form is, yes, in terms of is this. So next one is this. This is 6 by 4. I also write this also. Then of course A equal to B. You get the 2 left hand side, T and X, T and Y, T and Z, both are T and so I just equate the 2, this one, this right hand side, this right hand side. So what will you get if you write down ln x y ln is common. So I can write like this, bring it 1, this one, supposing this one is on the right hand side. So this into this is on the right hand side, this into this is on the left hand side. So now since this vector is common, so I want to write down, and so I can bring in minus this, minus this, minus this, because rest of the places all are zeros. And then I get a homogeneous, this is homogeneous. Homogeneous means, right, what is a homogeneous system of equation? b equal to 0, Ax equal to b, right hand side b is 0. Standard form of algebraic equation is Ax equal to b. So, this is right hand side is 0. So, here is this. So, we get 3 equations in 3, of course, these are all unknowns. I do not know, I have to find out the direction cosine, because I am only saying let n be the principal plane. So, what is that principal plane? I have to define. So, all these 3 are unknowns. So, we cannot, can we solve, now do not see this bottom one, bottom line do not see. Can we solve now, this is what we have got. Now, this is homogeneous. Can we solve this for ln x, ln y, ln z? Yes or no? 3 equations, 3 unknowns. What are the 3 unknowns? This. Here what is unknown? Sigma star is an unknown. So, there is also one. So, there are 4 unknowns and only 3 equations. Actually, there are 4 unknowns, 1, 2, 3 and sigma star. And only 3 equations are there. Plus, and this equation also is homogeneous. You know, Ax equal to 0 cannot be explicitly solved. You can solve only as a relative value. You have to assume one value, and in terms of that value you can solve the remaining n minus 1. You cannot solve explicitly. I think that you must be knowing. So, we have forgotten, let us not forget, because we have to look for one more relation, and one more relation comes from here. All the square of direction cosines must be equal to 1. The direction cosines, L square plus m square plus n square, I think you must have done, equal to 1. So, then that means, yes, it is okay now. So, we will have to have this total system to be solved for 4 unknowns. So, this is 3 plus 1, 4. However, since these are 3 homogeneous equations, one condition I have written, however, one condition must be satisfied. And whenever you have a homogeneous system of equation, you must have, remember, see, normally when it is a non-homogeneous equation, the A matrix determinant of A should not be equal to 0. If you want to solve Ax equal to b, you can get solution provided determinant of A is not 0. If determinant is 0, then you cannot get solution. But if Ax equal to 0, if Ax equal to 0, then the condition is that determinant of A must be 0. Then only you can get relative solution. You read algebraic equations, small theory is there. You can refer to Kreiszyk book, Kreiszyk, Advanced Engineering Mathematics by Kreiszyk. We follow it here. Kreiszyk, spell, I will write it here. Kreiszyk. Okay, and not only one, because it is a textbook for our undergraduate, so there must be about 30-40 copies in the library. So, the condition is, since it is a homogeneous 3 systems, 3 apparently 6, 5. Is the determinant of that matrix should be set equal to 0. this determinant should be set equal to 0. And if you write down this determinant, expand it 3 by 3, not very difficult. 3 by 3 means this into minor of this is this. So, this into this minus this into this, that is what we do know. How do we expand a determinant? This and then remove this row and this column, whatever is left is this, then this multiplied by minus this multiplied. So, you go on writing similarly this one, next one. So, next one, this one will go second column and second row, what is left is this and this. Then again this multiplication and this multiplication. Second one plus or minus, minus, second one minus, then third one again plus. Okay. So, so anyway, when you expand this, I will get, and this one will occur because this multiplied by this into this. So, this into this will give you a square and then multiplied by this. So, you will get a cubic equation in sigma star, and the cubic equation I have just written here. Final form I have written, I have not written the complete multiplication. So, this is what you will get. After when you do this, you will get a cubic. So, sigma star cube minus I1 sigma star square plus, now all this let it be sin be as it is, the way I have written. Then I2 means some coefficient, I2 multiplied by sigma star minus I3. This is the complete cubic equation, where I1 is given by summation of normal stresses. It turns out that I1 becomes this coefficient is nothing but 1, 2, 3, just normal diagonal one sum. So, it is this one are sigma x, sigma y, sigma z. I2 is this. Now, let us see what is this. I2 is this. So, I2 looks like, see, this one is minor, minor means this is called minor, na? Yes. So, if I remove the third column and third row, so I am left with this one, this one, this one. So, that is what is, of course, without sigma star. So, tau xx, tau yx, tau xy, tau yy. So, this sub matrix plus second row, second column. Now, first remove this last one, third row, third column, the first one. Second one, remove the second column and second row. Then you are remaining tau xx, tau zx, tau xz and tau zz. Okay. Plus only. Here no minus. Plus third one, remove the first column and first row. So, you are left with this yy, zy, yz and zz. So, this one you remember, please start from third, second and then first, not first, second and third. Then of course, if you start from first you will get this, it is okay. If you start from first, then you will get this, then second you will get this. So, value will remain the same. So, you get these three sub matrices 2 by 2. 2 by 2 is very easy to find out. So, this into this minus this into this into this minus this into this, and see somehow what is happening. It is normal stress, normal is here also, it is normal, here also normal. So, always on the diagonal you have normal stress. Diagonal is always containing a normal. So, normal stress, so I have just written here tau xx, tau yy minus this into this is this into this. Since this is symmetric, now we can take symmetric. Stress tensor is symmetric, xy yx. So, minus xy square. Then this xx zz minus xz square. then YYZZ minus YZ square. Yes, this one. So, if you expand this, you will get this. These three submatrices 2 by 2 can be expanded and then you will get this. If you want to write down in terms of sigma and tau, they will look like this. Can you read the last line? Written in little thin, okay, it is visible. So, then if you want to use sigma and tau both, then it can be like this. So, I2. So, this coefficient is defined now, this coefficient and this coefficient also I3 is nothing but determinant of our stress tensor. I will show you. Third one, is this only, determinant of your stress tensor. So, it is very easy to remember that to find out the principal direction, you get a cubic equation, you have to solve a cubic equation, and the cubic equation you have to write down as sigma cube minus I1 into sigma square plus minus interchanges I2 into sigma minus I3, and these three I's can be found out from the stress matrix. I mean sorry, yes, stress matrix or stress tensor. And now this one, you have to expand if you want to get determinant. So, if you want to expand, it is like this. Now, it so happens that at the same point, we will prove it also. Same point, see, same point means you have one plane on which these 9 components are corresponding to one plane, 9 components are working. Again corresponding to next plane, another 9 components are same point, point is same. So, let us say x, x dash, x double dash, x triple dash, there are all the directions. Now, it will so happen, it can be seen that these 3 I's they remain the same, they do not change by changing the orientation of the plane. Values of x tau ij changes, but these I1, I2, I3 remains the same for every orientation of the plane. So, they are called stress invariants. So, I1, that is for that reason they are called stress invariant, it does not change with the orientation of the plane. So, it is a very good property, we can prove it also, we will prove it. Prove it means take two directions and x and x dash and write down and then show that yes, both are same. Okay. So, this is independent of coordinate system. Now, yes, in our time solution of cubic equation was difficult, but now I think it is easy. We knew how to solve a quadratic equation. The moment it became cubic, it was very difficult. Cubic means if you can guess one root, then x minus that root you divide from the cubic and try to get your quadratic. Then you use quadratic formula x1 x2 equal to minus b plus minus b square minus 4ac divided by 2a. So, that was the method, but how to guess one root? So, it was always a method of trial and error. Somehow guess, do 3, 4, 10 guesses and try to get one root. But nowadays I have been told that it is there in your in your calculator, it is there solution. So, you can solve this cubic. So, this used to be a standard problem for in our time, that means find out the principal direction given the state of stress at a point. Find out the principal direction and principal stress that used to be there, because basic thing was cubic equation. And okay. Now, after getting the, see, this one will give you root of the cubic equation will give you sigma star. There will be 3 values. So, that is what I have written 3, 3 values. It so happens that these roots are always real, they are not complex for any real life problem in our. So, they are all always real, but then I have to also find out not only sigma star, but also ln x, ln y, ln z, the direction, what is the plane, I have to define my plane. So, and you see na, because you will be having a cube, not cube, I mean parallelepiped. So, one direction, let us say this is the principal direction sigma 1. So, this is sigma 2 and this is sigma 3. On the 3 planes, this is x plane, let us say you got it sigma 1 maximum. This also, this will not be maximum, but it will be also on that coordinate plane, there will be only one sigma, no shear, because if there is no shear here, there cannot exist a shear here. If there is no shear this, there cannot exist a shear here, complementary, shear is always complementary. So, there has to be only normal. So, you will get 3 normal values, one here, one here, one here. So, now we want to find out what is this direction. So, direction means, let us take this sigma 1, one of the, substitute sigma 1 in this, old one was there na, your homogeneous equation was there. So, I now substitute the value of sigma star, that is known quantity. So, now this matrix is known completely, earlier it was unknown, now it is known multiplied by, but still I cannot solve it because it is homogeneous. So, I add this 2. Now, how to solve? There are only 3 unknowns and 4 equations. Now, we have dependent, only 2 are independent, only 2 are, see, dependent means these 3, see, the very fact that this is equal to 0 means it is it can be proved that these 3 equations are dependent. Dependent means at least one equation can be obtained by combination of the 2, addition, subtraction, multiplication, something third. So, it is not independent. So, what we do, we take any 2 out of this and then this, because this is independent, this L square, M square, N square is independent. So, we take this. So, that is what I take 2 equation from set 1, this is set 1 and 2, and solve for direction cosines. Now, this is a little lengthy process, but you have to do it. This is, it has to be done. So, yes, so we can solve it and we get both direction as well as the value, both principal stress and the corresponding direction cosines can be computed. Next time you substitute here sigma 2, then get the direction cosine. Next time you substitute sigma 3 and then you get this. So, like this it is done. This is a very important part of our design process, because we are always interested in what is the maximum, not just okay. So, this completes computation of principal stresses. No, what about shear stress? Okay. So, next time, okay, we stop here. and but this is what is done in three-dimensional principal stress computation. Okay.